Welcome to a lesson on solving systems of linear equations using the substitution method. The substitution method is an algebraic technique for solving a system of equations. It's important that we have algebraic techniques for solving a system because sometimes graphing is impractical. The substitution method gets its name because we perform substitution in order to solve the system. Remember, the solution to a system of equations is an ordered pair that satisfies both equations. To understand how this process is going to work before we formalize our steps, let's consider the given system of equations. Notice how the first equation we have y equals 2x. Since y must equal 2x, let's consider what happens when we substitute 2x for y in the second equation. So if we perform this substitution, the second equation would be x plus, not y, but x plus 2x equals 3. So by performing this substitution, we get a single equation with a single variable which we can now solve. X plus 2x equals 3x. So we have 3x equals 3, dividing both sides by 3. Notice how we get x equals 1. So for our ordered pair solution, the first value is going to be 1. Now that we know that x equals 1, and we also know y equals 2x, because that's one of the given equations, if we substitute 1 for x, we'd have y equals 2 times 1, and therefore y equals 2. So the solution to this system is the ordered pair 1, 2. And let's take a moment and verify this. So we'll substitute 1 for x and 2 for y in both equations. So for the first equation, we would have 2 equals 2 times 1, which is true. And for the second equation, we would have 1 plus 2 equals 3, which is also true, verifying our solution is correct. But going back to the system just for a moment, this worked out very nicely because notice how one of the equations was solved for y. But in many cases, we won't have one of the equations solved for one of the variables, and therefore we'll follow the steps given below. Let's look at an example and walk through each step. For step 1, we solve one of the equations of the system for one of the variables. So looking at our system here below, notice how it would be easiest to solve the second equation for y because we can solve for y in one step. If we solve for any of the other variables in either equation, it would take 2 steps, and we might end up with fractions, which would complicate things. So for step 1, let's go ahead and solve this equation for y. So we'll subtract 2x on both sides, which would give us y equals 20 minus 2x. So this was step 1. Step 2, we want to substitute the expression for the variable obtained in step 1 into the other equation. So because we solved this equation for y, and we know y equals 20 minus 2x, we'll substitute 20 minus 2x for y in the first equation. So when we do this for step 2, we would have 3x minus 2 times not y, but 20 minus 2x, and then equals 16. Step 3, we want to solve this equation. So we would clear the parentheses by distributing. Because of the subtraction, we would distribute negative 2. So step 3, we'd have 3x minus 40 plus 4x equals 16. Combining like terms, 3x plus 4x is 7x. Adding 40 to both sides, we'd have 7x equals 56. Dividing both sides by 7, we have x equals 8, since 56 divided by 7 equals 8. So now we've made some good progress. We know that the x value must be 8, but remember the solution is an ordered pair. So for our solution, for the ordered pair, the first value is going to be 8. Step 4, substitute the result back into one of the original equations to find the ordered pair solution. So we want to substitute 8 for x into one of the equations here. Let's go ahead and use the second equation as substitute and substitute 8 for x. So for step 4, we would have 2 times 8 plus y equals 20. 16 plus y equals 20. Subtracting 16 on both sides, y equals 4. So our ordered pair solution is 8, 4. Step 5 says check the result into both of the original equations. So we'll substitute 8 for x and 4 for y in both of these equations here. So for the first equation, again step 5, we'd have 3 times x, which is 8, minus 2 times y, which is 4, equals 16. So 24 minus 8 equals 16. 24 minus 8 is 16, so our solution works in the first equation. And now for the second equation, we would have 2 times 8 plus y is 4 equals 20. We have 16 plus 4 equals 20, which also checks. Let's look at another example. Again, our first step is to determine which equation to solve for which variable. And notice how it's going to be easiest to solve this second equation here for x by adding 2y to both sides. So if we add 2y to both sides, we have x equals negative 3 plus 2y. So this is step 1. Step 2, we'll substitute negative 3 plus 2y for x in the first equation, which would be here. So for step 2, we'll have 5 times the quantity negative 3 plus 2y minus 4y equals 9. Step 3, we want to solve this equation, so we'll distribute 5 here and then solve for y. So we'd have negative 15 plus 10y minus 4y equals 9. Combining like terms, here we have 10y minus 4y, that's 6y. So negative 15 plus 6y equals 9. To isolate 6y, we would add 15 to both sides. 9 plus 15 is 24, so we have 6y equals 24. Divide both sides by 6. 24 divided by 6 is 4. So we know y is equal to positive 4. So for our solution, which we know is going to be an ordered pair, the second value will be 4. Step 4, we want to substitute this value here for y into one of the equations to determine our ordered pair solution. Because we're trying to find the value of x, let's use equation 2. So for step 4, using equation 2, we'd have x minus 2 times 4, because we now know y is 4, equals negative 3. So x minus 8 equals negative 3. Adding 8 to both sides, x equals 5. So our ordered pair solution would be 5, 4. Step 5, we want to check our solution, so we'll substitute these values into both equations. So for the first equation, we have 5 times 5 minus 4 times 4 equals 9. So 25 minus 16 equals 9, which is true. So our solution works in the first equation. And now for the second equation, we'd have x, which is 5, minus 2 times y, which is 4, equals negative 3. So 5 minus 8 equals negative 3, which is true. So we verified this ordered pair does satisfy both of our equations in the system. Example 3. First step, solve for one of the variables. Looking at example 3, notice how for our first step, it'll be easiest if we solve this first equation for y. So if we solve this equation for y, we would subtract 3x on both sides. So y equals 5 minus 3x. This would be our first step. Step 2, because we solved this equation for y, we want to substitute 5 minus 3x for y in the second equation. So step 2, we would have 6x plus 2 times, for y we're substituting 5 minus 3x. This is equal to positive 11. Step 3, we solve this equation, so we'll distribute here. So we'll distribute positive 2. So step 3 would be 6x plus 10 minus 6x equals 11. Now here, when we combine like terms, something special happens. Notice 6x minus 6x would be 0. So when we simplify this equation, we get 10 equals 11. Well, we know 10 does not equal 11. This is not true. So whenever the variables drop out, and we have a statement that's not true, this indicates our system has no solution. So let's look at our last example, example 4. So looking at our system of equations, notice how the second equation here is already solved for y. So step 1 has already been done for us. For step 1, we already know y is equal to x plus 1. But because we're using the second equation here, we'll now substitute x plus 1 for y in the first equation. So step 2, we would have x minus the quantity x plus 1 equals negative 1. Step 3 is to solve this equation. We need to be careful here. If it's helpful, we can think of having a 1 here, and therefore to clear the parentheses, we'll distribute negative 1 because of the subtraction. So step 3, we'd have x minus x minus 1 equals negative 1. Notice here the variables simplify out again. X minus x is equal to 0, so this simplifies to negative 1 equals negative 1. But notice here we have a true statement. Of course, negative 1 equals negative 1. So whenever the variables drop out and we have a true statement, this indicates we have infinitely many solutions. So in this lesson, we saw all three types of systems of linear equations where it's possible to have one solution, like example 1 and example 2. It's possible to have no solution, like example 3. And it's also possible to have infinitely many solutions, like we see here in example 4. I hope you found this helpful. We want to solve the system of equations and write the solution as an ordered pair. So we have a system of two equations with two unknowns, and we'll first solve this algebraically using the substitution method or elimination method, then we'll also check our solution graphically. So looking at these two equations, notice how we can solve this first equation for y by subtracting 5x on both sides. So because we have one equation that we can easily solve for one variable, let's solve this system using substitution. So again, our first equation is 5x plus y equals negative 11, and our second equation is 6x plus 5y equals 2. So the first step, we'll solve this first equation for y by subtracting 5x on both sides. So simplifying, we have y equals negative 11 minus 5x. So now that we've solved this first equation for y, we'll now perform substitution for y in the second equation, which will give us one equation with one variable, which we can then solve for x. So again, because y must equal negative 11 minus 5x, we'll substitute negative 11 minus 5x for y in the second equation. So we would have 6x plus 5 times the quantity in negative 11 minus 5x must equal 2. Again, notice how we have a single equation with one variable, and now we can solve this for x. Once we determine the value of x, we'll perform back substitution to determine the value of y. So here we'll clear the parentheses by distributing positive 5. So we have 6x, and then 5 times negative 11 is negative 55, so minus 55. And then 5 times negative 5x is negative 25x, so minus 25x equals 2. Let's combine the x terms on the left side. 6x minus 25x is going to be negative 19x. So we have negative 19x minus 55 equals 2. And now we'll add 55 to both sides of the equation. Simplifying, we have negative 19x equals 57. And now we divide both sides by negative 19. And simplifying, we have x equals negative 3. Now that we know x equals negative 3, remember our solution is an ordered pair, so now we'll perform back substitution to determine the value of y. And we'll go ahead and use this equation here that's already solved for y. Again, if we know y equals negative 11 minus 5x, then we know y must equal negative 11 minus 5 times the value of x, which we now know is negative 3. So we have y equals negative 11 plus 15, which equals positive 4. So we have y equals positive 4, and therefore the solution to our system of equations would be the ordered pair x comma y, or in this case, negative 3 comma 4. Which again means this ordered pair would satisfy both of the equations in our system. And let's take the time to check this algebraically as well as graphically. So we'll substitute negative 3 for x and 4 for y into both equations just to verify it would satisfy both equations. So for the first equation, we would have 5 times negative 3 plus 4 equals negative 11. Negative 15 plus 4 equals negative 11. And negative 15 plus 4 is negative 11. So the ordered pair does satisfy our first equation. And now for the second equation, we would have 6 times negative 3 plus 5 times 4 equals 2. Simplifying, we have negative 18 plus 20 equals 2, which does give us 2 equals 2, which is true. And therefore, we've just verified the ordered pair does satisfy both linear equations. Now to check this graphically, we could graph both linear equations, and because this ordered pair is the solution to the system, it would be the point of intersection, or the point that is on both lines. And to save some time, I've already graphed this. Here's the graph of the two linear equations, and notice how the point of intersection is this point here, where the coordinates are negative 3 comma positive 4, again the solution to our system of equations. I hope you found this helpful.